Congress longer than some of us are alive in this hall. And he's had his hands in many pies over the years. He was the original founder of GPLviolations.org, a group that helped getting the GPL tested in court. But he's not only inquiring in legal matters, obviously, he's also a technical guy. He founded Osmocom to get open source telephony stacks on the road. And today we are going to discuss how we can push billions and trillions of bits through a single line in a second, and not just do it on a physical level, but also actually get our application to understand what's going on. Welcome.
Yeah, thank you for the introduction, and thanks for the welcome. And yes, I think my first Congress was 15C3 or so it's been a while. Yeah, also short intro slide. I've used to be involved with Linux kernel hacking and the network stack, but I stopped doing that 15 years ago, so none of the work that I'm talking about today is something I created myself. I want to make that very clear. I've just used it, and I think it needs more users because it's amazing technology that has been put in place over the last 5 to 10 years. So yeah, my main focus is in another area in open source mobile communications, as has been mentioned before. As the t-shirt says, I like retro stuff. So that's why I'm also part of the team operating the ISDN and analog telephony network here at the event. So yeah, overview about the talk. First, a bit of context, then reiteration of traditional I/O models for processes on Unix-like operating systems and what kind of problem that creates, and then like 3 different sections, IOU ring, eBPF, and XDP. So I'm surprised as many people have made it to the talk, given the very acronym-laden title, and it's not even 3GPP related. So yeah, so it's a fairly technical talk. I expect some background in computer networking, operating system architecture, what system calls are, and the system call boundary between kernel and processes, and how the legacy BSD/POSIX APIs for socket I/O work. So you've been warned. Yeah, so the context in which this talk is intended is, well, we have programs doing network I/O. They have been doing that for, I guess, about 40 years. Of course, I didn't write code at the age of 5, so I don't recall 40 years ago in terms of development yet. But yeah, so BSD sockets have been around for ages. However, network speeds have significantly increased ever since, in case you didn't notice. And of course, CPU, RAM, and other things also have improved, but not to the same extent. And with networking, we have one aspect that it's not just the throughput, but it's also the packet sizes, and because there's of course a fixed overhead associated with processing any given network packet, and that fixed overhead is the same whether it's a 64-byte packet or whether it's a 1500-byte packet or a 9000-byte jumbo frame. So the MTUs, the maximum transmission units on networks, haven't really increased that much. So in transmission speeds, we've gone from dial-up modems with whatever 2400, 9600, whatever BPS to 100 gigabit Ethernet links today, or maybe back then first Ethernet implementations, ArcNet, token ring, whatever, but also gone to significantly different speeds. But the packet sizes haven't really increased with that. So the amount of packets per second we need to process has increased drastically. And if you look at classic network stack and sockets, what happens is, of course, a packet is received from the network interface card, then the kernel processes that packet layer by layer. We will look a little bit deeper in there, but of course first, in case it's an Ethernet frame, there is an Ethernet layer, and then there's the IP layer, IPv4 or IPv6, and then the TCP layer, and then there's a socket layer, and then that gets into your applications. And in that entire kernel processing pipeline, there are many different subsystems on Linux. There can be tunneling, there can be IPsec, there can be traffic shaping, packet filtering, network address translation, connection tracking, load balancing, QoS shaping, many different things, software bridging, whatever. At some point, the data gets enqueued into a socket receive queue of the program that we're looking at, and then that process gets woken up by the kernel scheduler because something is waiting in the receive queue for that socket, and the data then gets copied to the user space process. So that's sort of the lengthy thing that happens, and that needs to happen in case of at least datagram-oriented protocols like UDP or SCTP. That happens for every packet. For TCP, it's slightly different, but of course there are many applications that don't use TCP, particularly in my area of work. So yeah, this worked fairly fine with old modem speeds and so on, blah, blah, blah. I went through that. The result of this is that, of course, we have lots of different subsystems and lots of different pieces of code accessing lots of different data structures, and each of them likely means a cache miss, which likely means waiting for thousands of instructions for a memory to arrive. I don't have the figures right now, but a decade ago, it was fairly common that a CPU would wait about 9,000 CPU cycles for data to arrive from RAM if it's not in cache. And during that time, your CPU doesn't really do anything other than waiting for the data. I mean, yes, there's hyperthreading, but let's ignore that for a second. So yeah, a lot of time that gets wasted. Also, there's of course data copies of the data several times. At the very least, there's a copy when it gets copied from kernel into the user space process, because those are different memory segments and permissions and so on. So yeah, the other point is that the system call boundary is relatively expensive. So whenever you have a context switch between one process and another process, or even between a process and the kernel, that's a very complex, expensive operation. And it gets more and more expensive with all the CPU bug workarounds that we've been seeing during the past, I don't know, 5, 7, whatever years. So and of course, if other things get scheduled, the caches are no longer hot, and so on and so on. So it's all a bit problematic. Just to give you some context, for those working in networking, it's not new. This is just so you get an idea. If we look at 10 megabit Ethernet from, I don't know, 30 years ago or so, then we have a maximum worst case number of packets per second of 15,800. And today, if you look at 10 gigabit, that's 15.8 million. So we have quite a factor in between there. And with 100 gigabit Ethernet and so on, of course, it gets much worse if you look at the worst case packet per second that you need to deal with. So one thing to keep in mind is that we have to always separate between at least sort of two different use cases. One of it is the host case. That means the application is running on an end node that is either originating or terminating a packet. So you're sending something, it's a web server or a web browser or whatever, your DNS server, DNS client, whatever you want to talk about. They're end nodes, and there are different sort of aspects to this equation compared to all the intermediate devices like routers, firewalls, load balancers, middle boxes of any kind of sort. In the former case, with hosts and end nodes, we have application programs doing socket-based I/O traditionally, and routers, bridges, switches, and so on. Usually is handled inside the kernel. Of course, there are transparent proxies and application-level helpers and whatnot, but in general, that's sort of distinction. And solutions for those two also are looking slightly different. That's why there are many different parts that we look at. So in this first chapter of the talk, we will look at something called IOU ring. To me, really, it is the best thing that has happened to Linux kernel networking in, 25 years or so. So if we look at the traditional system calls you use to send and receive from sockets, that's like send, receive, receive from, send to, receive message, send message. Of course, there are many other derivations. You can also just use read and write. But in the end, you have some buffer of memory in your application, and you either want to transmit or receive. And that call, like traditionally, is blocking. So blocking I/O means your process is halted until that operation is completed, and then the scheduler transfers control back into the kernel. That, of course, only works for relatively simple I/O, and that's why there's many different ways of so-called non-blocking I/O. The traditional ones are select and poll and SE-poll, and we will have a brief look at them and how things evolved. So blocking I/O, the most naive way of doing I/O, the calling process or thread is blocked until I/O operation completes, only works in very trivial applications or applications that spawn lots of threads for I/O operations, which I also consider trivial because in many use cases you simply cannot have as many threads as you have sockets or I/O operations to deal with. So you can't really work in such a model if you really want to scale. Then, of course, the first step traditionally, if you read your your W. Richard Stevens Unix network programming or something like that, you have select. Select, well, has all kinds of disadvantages. For example, it only works for file descriptors less than 1024. It's not actually 1025 sockets, but the file descriptor numbers must be under 1024. And depending on how you open and close files, actually you might only have, anyway. So, don't do it. Yeah, you just shoot yourself in the foot. The complexity, I always have it in these I/O. So we have I'm not going to read the slide. You see it in front of you. So there is a complexity that depends on the number of the highest number of file descriptor that you have in your program. So it's relatively expensive if you have only few file descriptors of a larger set that you want to select on. So then there's poll, of course, from the BSD side. It's slightly better, so we just have O of n in terms of complexity. The kernel side code is mostly short with select. It's just the way how the user space process interacts with the kernel that changes here. ePOL was introduced a long time ago in kernel 2.5 versions. The complexity is reduced, so it's not O of the total number of FDs, but O of the number of ready FDs, those that have something to read or write. So complexity is slightly reduced, but fundamentally you're still doing one read or write system call for every read or write operation. And if you have hundreds of thousands of sockets, let's say, that you need to exchange information with, then that gets rather, unpleasant. One thing that is around, hypothetically, is POSIX AIO. That's asynchronous I/O specified by the POSIX definition. It has some really strange design choices, like notification of I/O completion uses signals, and writing code that's safe with signals, and yeah, it's not so nice. And also on Linux, it's a user space implementation in glibc using threads, so you really don't get any improvement. It's just a cosmetic layer on top of the traditional I/O that exists. Then there is libaio, which is not POSIX AIO, it's Linux AIO, but it only supports real files and not sockets, so it's not relevant for networking. And now in kernel 5.1, we finally have IOU-ring. As I put it here, it's literally the best thing since sliced bread in terms of I/O efficiency. The side effect, unfortunately, of introducing significant architectural changes into how system calls happen is that, lots of kernel exploits lots of bugs have been found and exploits have been made for bugs in that area. I think it has dried down now, so we had a lot of exploitable bugs in IOU-ring in the early days, but I think by now it's fairly quiet in that front. But some people decide that they'd rather be on the safe side, that's fine, but then they don't get the performance benefits of it, of course. So, okay, what is this all about? It's a memory-mapped submission and completion queue, or rather two queues, between the kernel and your user space program. So rather than having one system call for each and every I/O operation, you just say, well, I have this buffer of memory, and I want to have it written to this file descriptor, and then you put this as an instruction in a blob of shared memory, and the kernel will notice that you put something there, and it will execute that without any context switch whatsoever and without any system call requirement whatsoever. So it completely happens magically in the background, and when whatever I/O operation you submitted, or any of the I/O operations you submitted, completes, then a completion entry is put to the completion queue. And your user space program can now either poll that queue, busy waiting, or, of course, more intelligently, you can register an event file descriptor with your IOU-ring. That means when a read or write operation completes in the kernel, you will get a file descriptor that becomes readable, but you don't actually read the data from the file descriptor, but this file descriptor is just a mechanism how the kernel tells you, well, some of your I/O operations have completed, please check your completion queue. and then the process goes and can basically read thousands of entries from the completion queue just by having one system call, which is this waiting or reading from the event file descriptor and then processing thousands of completion events. And for submission events, there's not really any need for system calls at this point. So you can have basically an asynchronous queue of system calls, and actually it's not just I/O. It started with I/O, but by now you can do all kinds of things. So more and more system calls get added to IOU-ring. So I think eventually we will end up at a time or at a moment when you can do most of your systems calls in an asynchronous submission queue with completion events, and you don't have all these expensive kernel user space transitions all the time anymore. It's difficult for some system calls, but you see over time more and more get added. So a visualization of this, which slightly somehow, well, it's just the kernel, just the word kernel is cut at the bottom. Sorry for that. But yeah, so we have these rings on the submission side and the completion side, the kernel at the bottom, the application at the top, and the application just appends new records or entries to the submission queue. The kernel pulls them from the other end of the queue, and the same process happens the other way around from the kernel to the application. Yeah, you do your operations like this. So you serialize basically your system call by describing the system call that you want to do in a data structure, and then submit it to IOU-ring. The way how you use it usually is using liburing, which is a library that's provided by the same developers who create the kernel-side implementation. So you don't have to deal with like putting the data structures together for the submission queue entries and so on, but it has helper functions for this from the liburing. Yeah, the most common functions you would use is IOU-ring setup to create an instance of such a U-ring, and after you submitted some entries to the submission queue, there's IOU-ring enter, where you tell the kernel basically something is in the queue, please go and work on it. And yeah, completion events, as that, can be notified using event FD, which is very useful also if, let's say, you have a complex application that has many different libraries and dependencies, and some of your I/O you start to convert to IOU-ring, but you still have other I/O that uses normal socket interfaces, and so you still have a poll or select loop like you had before. And all of the stuff that you have ported to IOU-ring, you just register that event FD with your main poll or main select loop. So you can have basically from a single program, you can have IOU-ring I/O and legacy I/O very tightly integrated and very nicely without the need to port everything over to a new API or to move away from your traditional main loop, select or poll, whatever you're doing in your application. Yeah, as I mentioned already, more and more opcodes get added over time. So the opcode is basically like the system call number, basically the kind of operation that you want. Initially it was really just read and write, and now all the I/O stuff, but many others have been added. I haven't really used other stuff, but I think you can also create files now and all kinds of things. So yeah, I've been going through the exercise of converting the libraries we use for network I/O in the Osmocom project, or I started at least, not just my work, to IOU-ring, of course, a team effort. In our use case, we often have applications that deal with small I/O with thousands of peers or even tens of thousands of peers or more. And the packets that we deal with, they are often much smaller than the maximum transfer unit. So this is not like bulk file copying, but it's sending and transmitting lots of, let's say, 100 byte or maybe 200 byte large messages to thousands of peers out there. That's a typical telecom use case, and a lot of it is not TCP-based, but it's either SCTP or UDP as a transport protocol. And even if it's using TCP, the window is never full because we're not doing bulk transfer, and it's not a stream, but we're sending individual signaling messages that are very small. And we converted many of our libraries now over to IOU-ring, and the performance gains we see in real-world deployments is at the order of at least 50% CPU reduction compared to before. Often it's 70%, because if we looked at the profiles, and I think I have some slides. So this is a perf trace from Osmo BSC on a not so loaded. You see, it's like 18% total CPU. But I mean, if you look at it, the center column, you see almost all the CPU cycles are in the kernel, and almost nothing is in the user space program Osmo BSC. all of it was just this system call, entry, exit, and socket polling, and TCP polling, and do TCP poll, and do system poll, and whatever. So a lot of stuff that relates to this frequent system call, entry and exit. This is, ignore the blue one, I only have a graph that has two different plots in it. It's about a green plot. So at some point the process was started carrying load in the classic select classic poll and socket I/O read-write use case, and we had 70% CPU utilization, and then the same load, the process was restarted with the IOU ring backend, and you can see the CPU load goes down to 20% with the same workload. So it's quite a massive improvement for doing this type of I/O. It will not help you as much if you're doing bulk data transfer, so that will be a different picture. So this is a use case, of course, that is particularly particularly good for IOU ring. So I approached this, I first learned about IOU ring because I still follow what's happening in the kernel networking community. I always wanted to use it in a project, but of course we never really had much in our mobile communications world. We never really had much in the stuff that we do, the kind of super high performance requirements. But then we had a use case for GTP load generation. I wrote some code there. I also wrote an RTP load generator for media, RTP media streams. Both with IOU ring, and it was, I don't have the figures here, it was also quite promising, and that then triggered me to port the libraries that we have for I/O over. And conceptually, the problem was that our existing libraries, it's called select.c, but it did poll, so it's just the file name was basically still not renamed, even after many years switching from select to poll, in case you're wondering. So the problem is that what we had in place in the libraries was just a notification mechanism, but every application itself then would do its read and write itself. And that, of course, is problematic if you move to an asynchronous model, where suddenly all of that needs to happen underneath. So let's see an example of the old code. So we have something called an Osmo FD, a file descriptor abstraction that gets set up in the main program somewhere. We say we want to read from this, and we have a callback function that gets called whenever something is readable from the socket. And then in that callback function of the application, not the library itself, we actually perform a memory allocation, message buffer allocation, and then the read system call, which reads from the socket. And in this case, it's very, very hard to convert your application to Osmo, too much Osmo, to IOU ring, because in IOU ring, your I/O needs to be done entirely inside your I/O abstraction because it's happening asynchronously. You can't get a notification that something is readable, but you get the notification together with the data that has already been read from the file descriptor. So when you submit a read request, you pre-allocate some memory, and then you enqueue a read operation with the memory buffer, a pointer to the memory buffer, and the length, maximum length in that buffer. And then the kernel and IOU ring basically takes care of doing the I/O, and whenever it's ready, it will tell you it's ready. So you can't really work at that level. So all of this needed to be converted, and I'm going to spare you of some of the details. I just wanted to show a couple of lines of code so it's not entirely abstract. So we created an I/O layer abstraction, new one in libosmo core called Osmo I/O, which then has different backends, one for poll and one for IOU ring. And using an environment variable, you can switch over. So it's very easy to run the program with legacy socket-based interface and with IOU ring and make comparison between performance and also between functionality. So you can run your test suites against the old and the new code this way. And in the new code, it's basically your callback function. Note the function signature of the myRead callback. The message gets already passed in there. So you don't issue a read call anymore. That is done by a lower level, and you get the data that has been read. And in this case, it's passed as a message buffer, which is a data structure we use in Osmocom that's not really needed. Okay, yeah, details that you don't need to worry about. So the summary before we move to other topics is, well, IOU ring is a specific solution for optimizing the kernel user space interface for I/O. not just networking. You can do file I/O and you can do many more things now these days. It drastically reduces the number of system calls you need, which means much less context switches, much more cache locality, and so on. It still retains the same semantics. The operations are still, like the operations you put in the queue is still a read system call. It's just you don't call the system call anymore. You enqueue something that describes the read. But in the end, it's the same level of abstraction, the same interface, and the same semantics. And it's asynchronous. So, but even if you do that, of course, your packet still goes through a lot of kernel code before, right? All you're optimizing is the kernel to user space interface. So you still have your Ethernet driver doing DMA of the packet. Then you have the Ethernet stack parsing the Ethernet header. Then it goes in the IP stack, it parses the IP header. It goes in the TCP stack, it parses the TCP header. It goes through net filter hooks, it goes through all of those things. And only at the final end, when you enqueue things in the socket queue, then the transition into user space, that is what is optimized by IOU ring. And that can give you, depending on your application, already significant gains. But if you want to go beyond that, we need to look at other features, and that gets us into XDP, AF, XDP, and eBPF, which are kernel features at a completely different level for high-speed packet processing. Just the acronyms expanded, so XDP is the express data path, AF XDP is the address family for that, like AF INET or AF packet, and eBPF is the evolved Berkeley packet filter. Let me, before we look into this, contrast that to, I call it so-called solutions like DPDK. You may have heard of them, you may have used them. The idea of this is that you basically remove an entire network interface card from your Linux operating system and memory map basically its registers and whatnot into the user space program, and you do all your operations at the physical level, in case it's Ethernet, an Ethernet card, inside the user space program. That means the entire network interface card is removed from your operating system, and you're basically not using Linux anymore at that point. Which is fine. I mean, you can do that, but it also means you can use none of the features that Linux has for all of the packets arriving on that network interface card or that you need to transmit. So it's the entire NIC that gets removed. If you want to do that, that's fine. It gives you very high performance, but the kernel hackers came up with something that sort of is a compromise between the two worlds and is in mainline. It's in the kernel since 4.18. And it's called XDP. So the idea is that very early in the packet processing, just after a packet was received, we have the ability to register some kind of small program that decides whether we should take the normal slow path through the existing kernel stack or whether we do some processing that can be very quick without traversing all the entire stack and wasting all the CPU cycles and cache misses and so on that are associated with querying the routing table and all kinds of stuff. So, and this program basically can return a verdict, either drop or pass or TX or redirect, meaning that you can decide to drop the packet. So let's say you have some DDoS whatever protection mechanism, and based on whatever information that you have out of band, you can take a decision very early to drop the packet. Depending on your network driver, you can do that even before the normal SK buff, which is the in-kernel representation of the packet, is allocated in memory. So just when the DMA buffer basically is received from the NIC, you get this callback, and you can decide what to do with the packet. And if you say, I want to drop it now, it's dropped right there, and you don't ever even allocate the socket buffer or go anywhere through the kernel network stack. You pass is basically continue as usual, do as you were, and TX means transmit the packet, which you can modify there if you want, on the same or another NIC at that very early point in time. So for a bridge or something like that, it's a super efficient way to do this. You can parse the Ethernet header or whatever in your small program and look at it and then decide where to transmit it. And you can still have other packets that you pass through the normal part and so on. So this is a nice diagram. Sorry for being very small. It's not supposed to be readable. It's the idea of this diagram, and there's an SVG from Jan Engelhardt, it's on Wikipedia, so you can zoom in and so on. I'm not going to do this here. It's just the overview of what happens to packet processing in the Linux kernel. So if you receive a packet, it basically happens here at the left end. Your application lives here at the top. So if you receive a packet, there are all these different things that happen here and then up there until it finally arrives in the application. And that's what costs you all the CPU cycles and the efficiency. And if you forward the packet, basically it goes horizontally through all those different things until it finally gets transmitted at the output interface there. And with XDP now, at this very first location here, at the left-hand side, we have a small program that makes a decision whether we really want to take this expensive path, or we want to drop it, or we want to transmit it on another card. That's the line at the bottom. Thank you. The line at the bottom that bypasses all of this and transmits the packet on another network interface card. That's the fast path bypassing all of that. And then there's in addition something which is then AF-XDP, where you can have a socket that directly receives the packet, and that is actually here at that point. So the decision making happens here right after the packet is received, and you can basically say, well, this is a special packet, it belongs to some kind of flows which I'm handling in a special application that directly wants to receive the raw Ethernet frame without any of the processing through the normal kernel stack and so on and so on. So a very efficient way of receiving and processing packets, and you do the classification in your small program in front. AF-XDP. It operates on raw packets like AF packet, so it's not a socket for UDP or TCP. You have memory mapped RX and TX rings for 0 copy, so you can get the packets to this XDP socket with 0 copy, no copy between kernel and user space involved. You can use a single socket for transmit and receive, and you have descriptors in a ring in memory. You can also transmit the same descriptor that you just received, which means you can do 0 copy packet forwarding from user space. Right? It's not just like traditionally, if you want to do something, you had to do this in kernel, but with AF-XDP, basically some packet gets DMA'd into memory. You get your small eBPF, we will get to that point, program that takes the decision, says, well, I want this to go to the AF-XDP socket. And then just some descriptors to this is passed into user space, and the memory is mapped into user space, and you can then decide that this packet should be transmitted on another or the same interface again, and all of this can happen without any copy involved. So it's really rather interesting. Yeah. Now the question is, how do you write that small program for the decision making at that early point? Traditionally, you would have to write kernel modules, which is, not a very welcoming development environment, let's say, right? If you do something wrong, the entire machine crashes. So not everybody's favorite mode of doing things. However, these days, the Linux kernel has the eBPF virtual machine. Let me just make a very quick poll out of interest. Who knows what eBPF is? Or that, yeah. Okay, fine. So why are you here? Good. So eBPF can be used in many, many different applications, including very nice debugging and tracing tools and so on. But I mean, originally it was put in place for filtering if you use TCP dump filters and stuff like that, right? That's where BPF originates from. So the Berkeley packet filter, if you ever use TCP dump and you gave it a filter expression, that filter expression gets compiled into bytecode for a small virtual machine, which gets then sent into the kernel so that the actual filtering of the packets happens in the kernel, and you don't need to copy millions of packets to user space only to notice, the user actually requested me to not show this show this packet and drop it. So that's how it has been working for decades. And now eBPF has been extended. That's the E, and it has all kinds of, like a just-in-time compiler, and it has an in-kernel verifier to ensure that the program is safe. For example, there cannot be any endless loops, or there cannot be any access of invalid memory, and so on. So there's a lot of effort into all this validation that the programs you can load this way are safe and cannot, crash or otherwise violate the execution model in which it operates. Right now, maybe it's already outdated, at least half a year ago, there was an effort inside IETF to standardize the instruction set architecture of this virtual machine, the eBPF virtual machine. I'm not sure how far that has proceeded. It's not a topic I've been following. And with XDP now you can write a small program, compile that using a Clang-based compiler, load that in the kernel, and it gets executed at this very, very early point at the XDP hook for the network card that you attach to, and you can do this decision making in there. There is additional support infrastructure for eBPF, how, let's say, you have a filter list or something like this that you configure from user space, and then the kernel eBPF code should act on the filtering rules that you create from user space. So there are data structures and mechanisms how user space programs can exchange these data structures with the kernel to help you. Those are, for example, eBPF maps for that. Okay, yeah, it's a key and value store between core programs that you have in the kernel and user space. There's hash array, radix trees, Bloom filters, and it also has per CPU counters for multiprocessor efficiency, so that every CPU core has a copy of the data structure. Particularly if, let's say, you want to do packet counting or something, for sure you want to have them per CPU and then only add them when you read them to avoid cache line ping pong and other ugly business. Yeah, so the combination, as I said, we have this eBPF program, you write it, you use the Clang backend to target the BPF virtual machine, then you load that into the kernel and it registers it at the XDP hook, and then this program decides whether you take the slow path, the fast path, or whatever you do. Of course, it's not just decision making, you can implement packet processing in there. So let's say you want to do some kind of simple rewriting, a static net of addresses, or whatever kind of modifications you have in mind, you can actually change the content of the packet before you pass it on from that program. You just have the packet in memory, you can do whatever you want to it. So many use cases that you can do this way. So the most simple example of an XDP example program that does exactly nothing is this program here, which basically, well, you just say, there's this XDP MD context that provides you some data in, that's a function signature, but you always return XDP pass, and it basically does nothing, but then always pass the packets through the normal kernel networking stack, so there is no change to the existing behavior, and in there you would put your program logic, you write it in C, you compile it for this BPF virtual machine, and you load it into the kernel. A more complex example would be here, where actually we create a map and a per CPU array of counters, and then we have a bit of code to actually, well, if I manage to scroll down, which somehow doesn't want to work here. Okay. Yeah, so we have the actual program, which then basically looks up an element from the map and it looks at the counter, and if it's every other packet, then it passes it through the normal stack, and if not, it does something else. So yeah, whatever logic you want to put in there, it's of course an artificial example program. So yeah, what kind of use cases do we have? On the one hand, you can of course write device drivers for AFXDP. I mean, for user space stacks. So if you have something like DPTK or VPP, which are these user space frameworks that traditionally removed an entire network interface card from your Linux machine, logically speaking, now you can use XDP as sort of the Ethernet driver to feed your packets into DPTK, and then you can decide which packets should go into a DPTK application and which into the kernel user space. Of course, stuff like load balancers, software switches, I think in Open vSwitch is still experimental that support DOS protection filters, intrusion detection systems, so Ricata is using it. And in my personal domain, there is, for example, eUPF, it's a 5G user plane function that uses eBPF and AFXDP to perform this function. User plane function is mostly a tunnel encapsulation, decapsulation system used in cellular networks. So that kind of use case is a very good match for what you can do with that. And usually you end up with something like you have a fast path in the kernel, which means you don't need to copy and not context switch and so on, and you have a slow path in user space, and the slow path means basically you go through either through the AFXDP path that is zero copy and bypasses the kernel network stack, or you can still have other packets that go through the normal kernel stack. So you don't have to make a choice at a global level, but you have fine-grained control. That's just basically what I said. In our world, where I'm coming from in open source mobile communications, for example, the GPU handling is the second bullet point here. This is what I already meant with the eBPF. So the user plane function is a good match. Another possible use case, we haven't implemented it yet, it would be RTP flow proxying, or there are so-called media gateway functions that are sometimes needed. And what they do is basically just rewrite headers of RTP packets left and right, because you have networks that are intentionally not routed, but you always have this proxy in between for RTP flows for your voice calls. Traditionally, this is done in user space with sockets, which of course is slow, as we just have heard. There are some people like FreeSwitch, which is doing this optionally with RTP engine out of tree kernel modules that you need to build and insert, and which do ugly things. And now there's a clean way to implement such things in a safe way, cleanly, without out of kernel patches or modules or stuff like that. Yeah, some further reading, links that you can follow. I particularly like this one, The Lord of the IOU Ring. I think it's such a nice name. There are some resources about these technologies. You can find lots of examples out there, make use of them. There are also language bindings for many of these technologies around. I've seen stuff for Go, I've seen stuff for Rust. I think Ruby.io has already been ported over to IOU Ring, so if you're using Ruby on a modern system, you might already use IOU Ring without knowing about it. To my personal sadness, Erlang didn't yet have introduced IOU Ring support, where I think lots of, Erlang is a lot of message passing, so it would benefit to the same order of magnitude as we have seen in our Osmo VSC in terms of CPU cycle reduction. So I hope they do it at some point. That brings me to the end of what I wanted to present about. We still have some time for Q&A. Thanks for your attention.
Thank you, Laforge. We do indeed have time for questions, so please queue up at the microphones. If you don't want to ask any questions and you want to leave, like a lot of people are already doing, please remember to do so quietly and be mindful of the people who want to listen to the Q&A. I can see the first person over at, I can see the signal angel, so let's start on the internet.
Regarding IOU Ring, did you use IOU Ring for device communication with a constant data stream like SDR-IQ streams or similar data? Did you see similar improvements as with the network?
We do not use IOU Ring yet in such use cases. So we have optimized those cases where theoretically we should benefit the most. So basically take if you can get 50 to 7% CPU cycle reduction in certain areas, then that's what you focus first. On the SDR sample reception, I guess you can also save a bit, but I don't think it's so significant also, because in SDR use cases, the actual software processing of the samples is taking so much more CPU cycles than the amount of CPU cycles you spend doing the I/O, that overall I wouldn't expect such a massive reduction in this scenario.
Microphone number 3, please go ahead.
Hello, excellent talk, thank you.
Well, thanks.
I have 2 questions. First question is that you said that the eBPF XDP program can decide to forward the frame to an AF XDP socket, right? So how does it decide which AF XDP socket to forward it to? Because there can be multiple of them open, right? Is there one socket per interface, or how does it work?
There is one socket per queue of the network interface card. So modern network interface cards have many queues, and you can open one socket for each of those queues.
And the second question is, there can be...
We have a lot of other people, so we'll loop back around.
Okay.
Microphone number 1, please.
Let's put a ring queue, a submission queue, and a completion queue. Yeah.
Please.
One question about AF XDP. Can you actually do zero-copy networking from the NIC to user space directly, or does the kernel have to allocate something like bounce buffers and copy them to the shared memory region? So going directly from NIC to user space and back.
As far as I know, it is zero-copy at this point.
Okay.
But I'm not, I mean, that's sort of, I mean, I didn't write the code, but that's sort of my understanding, yes.
Okay, thank you.
Microphone number 2, please.
Can you use AF XDP to pre-reserve space in front or behind the buffered frames so that you don't have to use gather for encapsulation?
Yeah, sorry, can't answer to that off my head, sorry.
Let's do the internet again.
How does XDP compare to the capability of some NICs that can execute filters on them before reaching the OS?
Well, of course, it's a very generic question, like which NIC exactly, doing what exactly. Of course, if you do things in hardware or in a dedicated processor inside the NIC, it's always faster than doing it on the main CPU, because by definition you're not doing it on the main CPU and you have multiple things that now run in parallel and do processing. One thing I didn't mention though, which relates to the question, there are actually NICs, at least one vendor, Netronome, where you can offload your XDP programs. So they have fully integrated that, and you can, the same XDP program that you would normally run on your host CPU after the DMA has happened, you can download that fully transparently without any additional tools or whatever. It's fully integrated in mainline Linux. You can push it into the NIC itself. I think at the moment they make up to 50 GE NICs, not 100 GE. I haven't seen those yet, or faster. But you can push the actual XDP program into the NIC, and then sort of you have the best of both worlds, and in a transparent way that is portable to run on a normal CPU in software or also on this special accelerated NIC.
Microphone number 3.
Hi, thanks for your insights. I wanted to ask, since you mentioned in the talk that more and more syscalls get converted to IO Uring, are there any interesting syscalls that are missing right now for you?
Not really for me, no. I haven't really looked at it. I mean, in my world, we mostly do I/O or CPU-intensive stuff in the application. So we don't really have much other system calls that are not I/O related. So for my world, it sort of does what it's supposed to do. But I'm sure, let's say, somebody who works in different field has different requirements.
So the networking is there.
Yeah, networking is all there. File I/O is all there. But I think at the moment there's a discussion in the kernel whether the clone system call should be in IO Uring, for example, and what the semantics of that are.
Yeah, sounds like a difficult one, but thank you.
Yeah.
Microphone number 1 again.
Hi, thank you for spreading the word. I'm a network researcher, and I have implemented a more or less a VPN or multipath VPN software, and I'm currently using the TUN-TAP interface for getting the packets. And I don't really like it because, as you might know, you only get one packet with every read from it. So my question is, would it be possible to use the IO Uring framework for TUN-TAP to get there more? And also, if it's possible, do you know if the OpenVPN people, for example, use it for the OpenVPN server? Because I think that would improve it a lot.
So for the first question, yes. I mean, with the TUN-TAP, you get a file descriptor for the read and write, and that file descriptor you can just use with IO Uring. So definitely yes to that question. The second question, I don't know, but I guess it's one grab away in the OpenVPN source code to find out if they use IO Uring.
Yeah, okay.
So.
Microphone number 3, please, again.
Yes, I would like to ask the eBPF. You mentioned that there were checks against infinite loops and things like that, and it seems like it's a rather unorthodox programming language. I assume it's not Turing complete, and because of that, I wanted to ask if the compilers are any good. You showed a C snippet, that seems like that could be an easy way to get performance problems if the compilers aren't that good.
Yeah, it's not an area that I have. There are other people with, and there's like a lot of research during the past many years has been going into this research and development, but I'm not part of that compiler and eBPF VM discussion, so I can't really comment on that. But yeah, there's a lot of attention to it and a lot of effort going to it. That's all I can say.
But do you personally ever want to write manually, or are you satisfied with the compilers right now?
I'm satisfied with it right now because I try to keep stuff very simple as well. I mean, in general, you don't really want to do super complex things at that point. If you really do super complex things, then I think it's the wrong location. So it's mostly some rather simple things like looking up some table and checking if the IP address matches, or stuff like that. And it's not a very complex thing.
Okay, thank you.
The internet has conjured another question.
Yeah, third question. Does AF-XDP support packets larger than the page size? Example, AMD 64 only supports 4K, which is smaller than the jumbo frames can be. In the meantime, it didn't 5 years ago.
I can't comment on that. As I said, I was not involved with developing this. I'm just a poor user, and I can't comment on. I don't know everything about it, so no. I guess it's something you have to research online.
Microphone number 2, please.
So if you were to implement something supposedly trivial like a static HTTP server, how would you handle opening files and accepting sockets with IOU ring?
Just the same way like you do it now, just that you enqueue the open and the read and the write and the accept and whatnot as operations in the submission queue, and you get them completed asynchronously. And if there are ordering constraints, you can express dependencies. So you can say this operation must happen before that, and you can chain them in your submission queue so that the kernel knows they must be executed in a certain order and they cannot be reordered.
Thank you.
And number 1 again.
You mentioned at one point SCTP protocol, which is a protocol I found super interesting and played around a bit with, but my impression always was that nobody is using it and it's kind of dead.
Are you using a mobile phone?
Yeah.
Well, the entire backend of mobile telephony uses SCTP everywhere. Well, not everywhere, but at least, let's say, in 4G everywhere, and even in 5G, all the signaling from the base station back to the network goes through SCTP.
Okay, cool.
So yes, it's not used, let's say, by the Joe random user at their personal internet connection at home use case, but it's used heavily by everyone using mobile data.
And what are the implementations or the operating systems? Are they all using Linux and the Linux implementation, or is this like some commercial telecommunication OS?
Well, a lot of them are using the Linux kernel stack, but then there are also a lot of them that use user space stacks that they bring themselves because they have developed them ages ago and they don't want to move somewhere else. There's a user space SCTP stack that also is typically used on macOS, as far as I know. So it's just a library that you link, and it uses raw IP sockets on the bottom and implements the SCTP in user space. I'm not sure about other operating systems.
Oh. Thank you.
Number 3, please.
I'm not sure if you touched that point, but how many slots are in the ring? When is it defined? How many are there? Or is it's like in the picture you had, it was static? So
yeah, so like when you create the ring, when the IOU ring, I forgot the exact call right now, but when you create the ring, you specify the size for the submission and completion ring. I'm not sure if you can change it later. We don't do that in our software, but we size it at the beginning. Well, yeah.
Okay. Thank you.
But I mean, you can have also you can create multiple rings. So even if, let's say, you could hypothetically, if you could not change the size of an existing ring, you can just create a new one that's larger, start using the new one, and when the last completion of the old one is completed, you remove the old ring. So you can also do it that way for sure.
Wonderful. Thank you.
We have a few more minutes left, so please don't unqueue anymore at the mics, and now we'll take number 4.
You mentioned that for IO-ring, the user space application just writes into a memory region. How does the kernel recognize that? I assume it doesn't do active polling or something like that?
Well, you have, from the application user point of view, you have this, this function of liburing that you use. What it does underneath, I can't tell you right now. I think there's some smart trickery. You can do a system call at that point if you want to, but I think it's just changed the memory, and whenever the process scheduler is scheduling, or when the kernel is doing something, I guess that's checked. I think it's doing something in the memory region that the kernel can detect independently at any given point in time, so without a kernel-to-user space transition, but I think there's also a way how you can explicitly say, well, yeah, now there is stuff, please go check.
Okay, thank you.
But I'm not entirely sure about all the internal details.
Number 2, please.
How do you test XDP programs? Do you have to spawn every time a whole system with the associated NIC and everything?
That's what I do. Yes, I mean, I'm not sure if there is a simulator or something, but I don't see a. I mean, you can always unload and reload the program. It's not like you need to respawn a system every time you test a new development cycle. You load your BPF program, you test something, you unload it again, you load it again, you unload it again, so you don't need to restart the system all the time, right?
And number 1, please.
Yeah, one question regarding IO-ring. Do you know how a fork affects existing IO-ring buffers and file descriptors?
It's a good question. I would suppose, I mean, file descriptors are basically in both, right? After you fork, the file descriptors are there, so I would expect the U-ring also to be mapped there. But I don't actually know, to be honest. We don't generally fork in the kind of like not at that later point. I mean, there might be some forking earlier, but not later in the runtime.
All right, thanks.
And with that, we have exhausted our submission queue. I would like for all of you to enqueue another round of applause for LaForge.